Module 1, Lesson 4 is all about relations. Module 1, Lesson 4 covers the following outline. The definition of relations, relations on a set, classifications or closures of relations, operations in relations, and finally, special relations. Relations, by definition, or relationship between elements of a set are represented using the structure called relation. Relations can be used to solve problems in determining which pairs of cities are linked by airline flights in a network or producing a useful way to store information in your computer database. One of the more effective ways to express a relationship between elements of two sets is to use ordered pairs made up of two related elements. For this reason, sets of ordered pairs are called binary relations. An example of relation on a set of numbers usually appear on this given particular form, whereby an element A, which is taken from set A, is paired together with another element B taken from set B. In this case, the relation given on this particular example is given off by this respective property, whereby the value of A would be equivalent to twice the value of B. Therefore, your corresponding relation would then contain the following ordered pairs. You have 2, 1, -4, -2, 6, 3, 8, 4, and so on and so forth. Another practical example of your relation is on a given particular ordinary deck of playing cards. If your corresponding relation contains this pair of cards whereby they have the same suit, therefore the following pairs of cards may be grouped together to form the following relation, whereby you have Ace of Clubs, King of Clubs, Queen of Spades, Jack of Spades, 9 hearts, 10 hearts, 2 diamonds, 2 diamonds, A relation may not be limited into pairs of elements. Groups of elements in your relation may contain 2 or more. Here, on this given example, taken from the same set or deck of cards, we have the following relation that forms winning hand in a game of poker. Therefore, it's possible to have what you call a pair. A pair comprises 2 cards of the same value. Therefore, it's possible to have Ace of Clubs, Ace of Hearts, Queen of Spades, Queen of Diamonds, or any other pair of cards with the same value. You may also have a winning hand this time comprising of 3 cards, thereby grouping 3 elements this time at a time, whereby it's referred to as 3 of a kind. Here, it's possible to have a winning hand whereby you have King of Clubs, King of Hearts, and King of Spades. It's also possible to have a winning hand comprising this time of 4 cards. Therefore, your relation would comprise of groups of 4 elements. So it's possible to have Jack of Clubs, Jack of Hearts, Jack of Spades, and Jack of Diamonds. And finally, it's possible to have a maximum number of 5 cards on a winning combination in your game poker. Here, you are given the winning combination called Full House, whereby you end up with a pair and 3 of a kind. It's also possible to have other winning hands that contains 5 cards. This time, you end up with what you call a street, whereby you have sequentially ordered cards in terms of value, and a flush, whereby you end up with 5 cards and they all belong to the same suit, or straight flush, whereby you have sequentially ordered cards and they all belong to the same suit. And finally, it's possible to have what you call a royal flush, whereby you end up with the 5 highest valued cards in your deck having the same suit. Another practical example showing you relations is by the use of your family tree or genealogical chart. Here, we could express relations by grouping names based from like marriage, from siblings, and parents, and so on and so forth. If elements on the same set are joined together to form relations, then that particular relation is called an identity relation or equality relation. It's also possible that you cannot form relations from your given set if your particular property is not satisfied. Hence, you end up with what you call a trivial, void, or empty relation, which consists of null elements. A binary relation from A to B implies a subset of A times B, whereby the ordered pairs of your particular relation are from set A going to set B. Hence, it's often denoted by this given notation, which is basically an element of your relation. For example, let's say set A contains 0, 1, and 2, and your set B contains A and B. Therefore, the relation from A to B may be the following ordered pairs. So you have 0A, 0B, 1A, 2B. Note that only these ordered pairs are the ones that are related, meaning if 0, A is present, therefore 0 is related to A. However, if 1, B is not included on the relation, although that is possible, then 1 is not related to B. Always remember that not all possible ordered pairs may be included in your given relation set. Relations can be expressed graphically using arrows to represent the ordered pairs. Hence, for this given particular example of our relation from A to B, whereby our corresponding ordered pair comprises of 0A, 0B, 1A, and 2B, it can be represented now as two sets with these corresponding elements that are joined together by arrows. Each of these arrows eventually represent a particular ordered pair, shown in your given relation set. Another way to represent your relation is to use table. So if we then represent our given relation from set A to set B, containing the following ordered pairs 0A, 0B, 1A, 2B, it would then appear like this, whereby the elements of your rows corresponds to your set A, and the elements of your column corresponds to set B. And the cells where they do intersect are marked with X if these particular elements are eventually related and seen on your relation set. A relation from set A to set A basically implies that it contains subsets of A times A. Therefore, your corresponding relation will eventually end up with 2 raised to m subsets. Let's evaluate then this example. Let's say set A contains values 1 to 4, and we're forming relations from set A to set A following this given property, that your element B divides element A with an integer quotient. Therefore, the following ordered pairs can be formed, whereby you have the ordered pair 1, 1, 2, 1, 2, 2, 3, 1, 3, 3, 4, 1, 4, 2, and 4, 4. Bear in mind, these are the only ordered pairs that eventually satisfy the given particular property, since A may be any value 1 to 4 and B may be any value 1 to 4. Likewise, you can also represent this relation graphically, looking like this. And you may also represent this particular relation in a particular tabulated manner like this. Let's evaluate that same example set A containing values 1 to 4, and this time form the relation whereby element A divides element B with an integer quotient. Therefore, the following ordered pairs can now be created. You have the ordered pair 1, 1, 1, 2, 1, 3, 1, 4, 2, 2, 2, 4, 3, 3, and 4, 4. If we illustrate this relation graphically, it would then appear like this. And if we tabulate then our relations, it would now appear like this. On this given example, we are asked to determine which of the following given relations do include the following ordered pairs: 1, 1, 1, 2, 2, 1, 1, negative 1, and 2, 2, bearing the following relations from set A to set A. As seen from our corresponding letter A, your relation R1 comprises of ordered pairs whereby the property is A less than or equal to B. For R2, this time the property is A greater than B. For R3, the property is A equal to B or A equal to negative B. And for R4, only A equal to B. On relation R5, it now contains the following ordered pairs whereby A is equal to B plus 1. And finally, on relation R6, we have the ordered pairs whereby A plus B is less than or equal to 3. Therefore, your ordered pair 1, 1 is included in R1, it's included in R3, it's included in R4, it's included in R6, while the ordered pair 1, 2 is included in R1, included only in R6. Then your ordered pair 2, 1 is included in R2, included in R5, as well as R6. Your ordered pair 1, negative 1 is now included in R2, included in R3, and included in R6. And finally, the ordered pair 2, 2 is included in R1, included in R3, included in R4. Classifications or closures of relations are actually dependent based from the ordered pairs that are actually included within your given relation. The first classification or closure is referred to as reflexive. A particular relation is considered to be reflexive if every element of set A is related to itself given by the corresponding ordered pair A, A. Therefore, your corresponding relation is reflexive if and only if it contains ordered pairs of A, A. Let's try to consider then the following relations on this given particular set, whereby you have set A containing values 1 to 4, and we're forming relations from set A to set A. We're given the following relation R1. As seen from this corresponding relation, R1 is not reflexive. R2, from this given ordered pairs, R2 is not reflexive, whereas R3, as seen from this corresponding relation, is reflexive, because your R3 contains the ordered pair 1, 1, 2, 2, 3, 3, and 4, 4. And according to the definition, an ordered pair can only be considered reflexive if and only if every element of set A is related to itself. Your R4 therefore is not reflexive, while your R5 is reflexive, since, again, As seen from your relation R5, it contains 1, 1, 2, 2, 3, 3, and 4, 4, while R6 is not reflexive. Another classification or closure of your relation is known as symmetry. In some relations, an element is related to the second element if and only if the second element is related to the first element. Meaning, a relation on a set is called symmetry if B, A is an element of your relation R, whenever A, B is an element of your corresponding set. Let us then evaluate this given example whereby we have set A containing values 1 to 4 and we form relations from set A to set A. If we then look at relation R1, R1 is not symmetric because R1 contains the value 3, 4, but it does not have its symmetry, which is 4, 3. If you look at R2, R2 now is symmetric because R2 contains 1, 2, and it also contains 2, 1. The ordered pair 1, 1 in itself is already symmetric since A is equal to 1 and B likewise is equal to 1. Therefore, the ordered pair 1, 1 may appear as A, B, or it may appear as B, A. Therefore, it contains A, B, likewise B, A. R3 then is symmetric. If you look at the ordered pair seen on your R3, you would see that it contains 1, 2, 2, 1, 4, 1, 1, 4. Therefore, this particular relation is symmetric. R4 is not symmetric, likewise R5 is not symmetric, and also R6 is not symmetric. The next classification or closure is known as antisymmetric. A relation on a set is called antisymmetric whenever A, B is an element of your relation R and B, A an element of your relation R, only if A is equal to B. That means a relation is antisymmetric if and only if there are no pairs of distinct elements A and B, with A being related to B and B being related to A, given off by the mathematical expression like this. Note that symmetry and antisymmetry are not opposites. This is due to the fact that some relations eventually have both, meaning they are both symmetric and antisymmetric, while some relations eventually lack both, meaning neither of this particular relation is symmetric, nor is it antisymmetric. Let us look again our given example whereby we take relations from set A containing values 1 to 4. R1 is not antisymmetric due to the fact that you have the ordered pairs 1, 2 and 2, 1. Likewise, R2 is not antisymmetric. R3 is also not antisymmetric, while R4 is antisymmetric. If you look at R4, you have 2, 1, but you do not have 1, 2. You have 3, 1, but you don't have 1, 3, and so on and so forth. So, if you look at then R5, R5 is also antisymmetric. Looking at the ordered pairs of R5, you will notice that only elements that have equal values like 1, 1, 2, 2, 3, 3, and 4, 4 are present on your relation R5, which makes it antisymmetric. And at the same time, you have 1, 2, but you don't have 2, 1. You have 1, 3, but you don't have 3, 1, and so on and so forth. And R6 also is considered to be anti-symmetric since it only contains the ordered pair 3, 4. The next classification or closure is known as transitive. A relation on a set R is transitive whenever A, B is an element of your relation R. Likewise, B, C is an element of your relation R. And then A, C is also seen on your relation R, whereby A, B, and C are simply elements of set A. Note that on your particular relation, any particular value may be called A, B, or C. This particular relation eventually implies that when you have A, B and B, C, the values of B are equal. And then when you have A, C, then these elements C's are all equal and A's. It is actually given up by this mathematical expression. Let us consider this example of relations which were taken from set A containing values 1 to 4 and determine which of the following relations are considered transitive. If we look at R1, R1 is not transitive due to the fact that you have the ordered pair 3, 4, 4, 1, and there is no ordered pair 3, 1 on your relation R1. If you look at R2, R2 is also not considered transitive, although on your relation R2, you can see that you have the ordered pair 1, 2, 2, 1, and 1, 1. However, if you interchange the position and place 2, 1 first, then 1, 2, you do not have the ordered pair 2, 2 on your relation R2. Relation R3 is also likewise not transitive due to the fact that you have 4, 1, 1, 2, but you do not have 4, 2. Relation R4, however, is transitive due to the fact that you have 4, 2, 2, 1, and you have 4, 1, 4, 3, 3, 1, you have 4, 1, 4, 3, 3, 2, and you also have 4, 2. Likewise, relation R5 is transitive because you have the ordered pair 1, 1, 1, 2, making up 1, 2, 1, 1, 1, 3, making up the ordered pair 1, 3, 2, 2, 2, 3, making up the ordered pair 2, 3, and so on and so forth, while R6 is not transitive. Operations in your relations. The first operation involved in your relation is called the inverse of relations. The inverse of your relation is given off by this corresponding symbol and is generally described to be a relation that contains B, A whenever your corresponding relation R contains A, B, which is basically referred to as the complementary relation of your ordered pair, which is, if you look at it, it's exactly the symmetry of your corresponding relation. If we then evaluate the inverse of a relation from set A to set A, wherein it contains values 0 to 4, let's say my relation G, which contains the following ordered pairs 1, 0, 2, 0, 2, 1, 3, 0, 3, 1, and 4, 0, the inverse of this relation now would be 0, 1, 0, 2, 0, 3, 0, 4, 1, 2, and 1, 3. Likewise, if we form a relation R from set A to set A, containing the ordered pairs 1, 0, 1, 2, 1, 3, and 1, 4, then the inverse of this relation would now contain 0, 1, 2, 1, 3, 1, and 4, 1. Since relations are subsets of A times B, therefore, you can combine relations in any way your subsets are combined. Let's consider then set A containing values 1 to 3 and set B containing values 1 to 4, and from which we form relation R1 containing the following ordered pairs 1, 1, 2, 2, and 3, 3. Likewise, we form relation R2 containing the following ordered pairs 1, 1, 1, 2, 1, 3, and 1, 4. Since R1 and R2 are subsets of A times B, therefore we can perform union of your relations R1 and R2, upon which the union of your relation would then be the ordered pairs found in R1 or in R2 or both. Therefore, your union of R1 and R2 would eventually contain the following ordered pairs. You'd have 1, 1, 1, 2, 1, 3, 1, 4, 2, 2, and 3, 3. Let us then consider this time intersection of relations. An intersection of relations would mean the ordered pair common between R1 and R2, which is in this case 1, 1. You could also likewise do difference of relations R1 and R2. So R1 minus R2 would then be equivalent to 2, 2, and 3, 3. And the difference of relations R2 minus R1 would then comprise of the ordered pairs 1, 2, 1, 3, and 1, 4. Composition of relations. Another way relations are combined is by composition of relations. If we then let A be a relation from set A to set B, and relation S from set B to set C, then the composite of R and S is the relation consisting of the ordered pair A, C, where A is an element of set A and C is an element of set C, for which there exists an element B such that B is an element of set B, and that element B is paired with your relation R in A, B, and that same B is included in your relation set S, whereby the ordered pair is B, C. In other words, the composite of R and S, which is technically denoted by this given symbol, is constructed using the ordered pairs in your relation R and the ordered pairs in your relation S, whereby the second element of the ordered pair in your relation R, which is technically element B, agrees with the first element of the ordered pair in your relation S, which is also element B. The pairs that do agree eventually make up the new pair A, C for your composite of R and S by taking the first element of the ordered pair in R, which is element A, with the second element of the ordered pair in your relation S, which is element C, similar to the closure transitive on relations. Let's take, for example, the composite of relation R and S, whereby relation R is taken from set A to set B, set A containing values 1 to 3, and set B containing values 1 to 4, forming the ordered pair 1, 1, 1, 4, 2, 3, 3, 1, and 3, 4. And then you have relation S, which is taken from set B to set C, whereby set B contains values 1 to 4, and set C contains values 0 to 1. Hence, your relation S now contains the ordered pairs 1, 0, 2, 0, 3, 1, 3, 2, and 4, 1. Therefore, the composite of R and S would then be 1, 0, 1, 1, 2, 1, 2, 2, 3, 0, and 3, 1. Another example would be this given particular composite of R and S, whereby your relation R this time contains the ordered pairs 1, 2, 1, 3, 2, 3, 2, 4, and 3, 1, while your relation S contains 2, 1, 3, 1, 3, 2, and 4, 2. Therefore, the composite of R and S would now contain the following ordered pairs only. You have 1, 1, 1, 2, 2, 1, and 2, 2. When evaluating powers for your relations then, we will then let R be a relation on set A, and the powers R raised to n, with n being positive integers, is inductively defined to be R raised to n plus 1, which is equivalent to the composite of Rn and R. This definition shows that these particular values are inductively defined, showing that you cannot solve R cubed without R squared. Let's try to evaluate then the corresponding powers of this given relation R from set A containing values 1 to 4, whereby your relation R contains the following ordered pairs 1, 1, 2, 1, 3, 2, and 4, 3. Therefore, your R squared value would now be equivalent to 1, 1, 2, 1, 3, 1, and 4, 2. Whereas your R cubed would now be the composite of R squared and R. Hence, your R cubed now would be equivalent to 1, 1, 2, 1, 3, 1, and 4, 1. Special relations occur if your corresponding relations contain 3 or more closures. One of the special relations is known as the equivalence relation. A relation on set A is called an equivalence relation if it is reflexive, symmetric, and at the same time transitive. Thereby, two elements are related by an equivalence relation are called equivalent. Let's take, for example, this corresponding relation from set A containing the set of integers to set A, whereby our relation contains the ordered pair A comma B with A equal to B or A equal to negative B. We'll then try to verify if this corresponding relation is indeed an equivalence relation. So we then check if this particular relation would then be reflexive based from our corresponding values seen on your relation. This particular relation includes 1, 1, 2, 2, 3, 3, negative 1, negative 1, negative 2, negative 2. Therefore, hence, it is reflexive. Likewise, included within this relationship, you have the following ordered pairs. 1, negative 1, negative 1, 1, which makes it symmetric. And at the same time, since all three of these corresponding ordered pairs are always present on your relation, therefore, this is also transitive. Therefore, this relation is then considered to be an equivalence relation. Another special relation is known as the partially ordered relation set. A relation R on a set S is called partial ordering or partial order if it is reflexive, at the same time antisymmetric, and at the same time transitive. Let's try to verify if this particular relation from set A containing the set of integers to set A is indeed a partially ordered set or poset. This particular relation contains ordered pairs of 1, 1, negative 1, negative 1, 2, 2, 3, 3, 4, 4, and so on and so forth, making it therefore reflexive. And if you look at the ordered pairs, this particular relation contains 2, 1, but it will never contain 1, 2. It contains 3, 1, but it will never contain 1, 3. Therefore, making it anti-symmetric. Even though 1, 1 is considered to be symmetry, remember, anti-symmetric means that symmetry only occurs if A is equal to B. And likewise, this particular ordered pair also contains 3, 2, 2, 1, and 3, 1, making it therefore transitive. Hence, this relation is a partially ordered set. A lexicographic order involves two posets or partially ordered sets, and the lexicographic ordering on a subset A1 times A2 is defined by specifying the values A1, A2, which is less than B1, B2. That is, if their corresponding values would be greater than or less than, then there is a certain arrangement that they are eventually written on your given relation set. This is so-called lexicographic ordering because this process follows alphabetical ordering of words similar to that of your dictionary. The words in your dictionary are listed in alphabetic order or lexicographic order and is based on the ordering of letters in the alphabet. Likewise, it may be ordered from given numbers. This definition can easily be extended up to lexicographic ordering whenever you. Let's consider then strings of lowercase English letters. A lexicographic ordering can be defined using the same ordering as seen on the letters of the alphabet. Therefore, the word discrete is actually ahead or written first than your discrete, because these strings eventually differ at the seventh position of the letters E and T. Obviously, E comes first before T. And then discrete comes first before discreteness, because the first 8 letters eventually of the two strings do agree. However, the second string turns out to be longer than the first string. Therefore, the shorter string comes first, as seen on your dictionary. We could apply the same process whenever we write down ordered pairs on your given relation. This is very common on all particular ordered pairs in any given relation. So this particular format, when writing down your ordered pairs in your relation, is more or less a general format. Let's say you have a relation R containing 3, 5, 4, 8, 3, 8, 4, 5, 4, 9, and 4, 11. What would be the correct lexicographic ordering for these following ordered pairs? Therefore, you'd end up with a lexicographic ordering of ordered pairs arranged as 3, 5 first, then 3, 8, 4, 5, 4, 8, 4, 9, and 4, 11.